How's it going, Professor Scott? It's Alejandro Zabella, and here's problem 4 of the final exam. So now problem 4 says, let's modify the exponential decay model with the following. Suppose there's a substance that decays at a rate, so the decay rate, let's call it dm dt at a rate that equals a third of the mass of the substance raised to the 4th power. Let's say we start with 10 grams of the substance. So m of 0 is 10. And the unit of time is years. And that actually was A, which is write the differential equation IVP that models the situation, include units and the initial conditions. So here's A. And we'll just add that mass M in grams and time T in years. So there's part A. Then part B tells us to solve the d. So if we go ahead and do that, dm dt is a third m to the 4th. This is separable, so I can just move the dt over here and that m term over there. Those are going to cancel. And I get, it'd be easier if I write it as m to the negative 4th dm equals a third dt. I can take the integral of both sides now. And m to the negative 3 negative third equals a third t plus c times negative 3 times negative 3 times negative 3 m to the negative 3 is negative t minus 3c. Now I can raise this to the negative third to cancel that. M is equal to negative t minus 3c to the negative third. And I know that when m is 0, the answer should be 10. M of 0 is 10. So 10 equals 0 minus 3c to the negative third. Raise that to the negative 3 to get rid of it, which means I have to raise this to the negative 3. 10 to the third is 100, is 1,000. So that's 1 over 1,000 is equal to negative 3c divided by negative 3, negative 1 over 3,000 is equal to c. So my solution is m equals negative t minus minus 3 times c. So just make it one term. If I know negative 3c was 1 over 1,000, I'll just leave it like that as 1 over 1,000 all to the negative third power. There's part B. And now part C says to find the half-life of the substance. Well, if we start with 10 grams of the substance, then half of it is going to be 5 grams. And that's going to be equal to negative t plus 1,000 to the negative 3. If we raise that to the negative third, raise this to the negative third, 5, let me double check in the calculator. 5 to the third is 125, so it's negative 1 over 125 equals negative t plus 1 over 1,000. Let's get some more lead out of this pencil. Move the 1 over 1,000 over. And let's go back to the calculator and do this in there. It says 7 over 1,000 equals negative t. Cancel that negative. And so negative 7 over 1,000 equals t, which means that the half-life is negative 7 over 1,000 years. But obviously that doesn't make sense because we can't have negative time. So I think, where's my mistake here? I think it starts right here, because if it's decaying, this should be negative, so that we have a negative rate, which means that this is negative, which means this is negative, which means that this is negative, come on, pencil, that's negative, so this is a positive t, this is a positive t, and so m is actually t plus 1 over 1,000 to the negative 1/3, which means that in actuality the half-life should be 7 over 1,000 equals t. So half-life equals 7 over 1,000 years. There we go. That's better. That was my problem. And so now we can keep going. And D, I'll go ahead and put that over here, says how long until there's only 1.5 grams left. So 1.5 is the mass. It's equal to T plus 1 over 1,000 to the negative third power that's, get rid of that power. Let's see, 1.5 to the third is 27 over 8, but it's negative, so then it's going to be 8 over 27 is equal to T plus 1 over 1,000 minus 1 over 1,000 on both sides. Let's do that in the calculator. 8 over 27 minus 1 over 1,000. It's just leaving me a decimal. It doesn't want to make it into a fraction. So let's just leave it there as that. 0.2953 equals T. So after 0.2953 years, there will be only, need more lead, 1.5 grams left. And then I break it. And there it is. Problem 4.